today we are starting to talk about one of our parent functions, the exponential function. So an exponential function is where you have x in your exponent. So we have our base, which we abbreviate as a, and your base is a number, so a to the x power. Now this a value is going to be positive because if we throw a negative in front of it, that's just going to indicate a transformation. And a can be any number except 1. Now let's think about why that is. If I raise the number 1 to any power, 1 squared is 1. 1 to the third is 1. 1 to the 1/2 is 1. All of those numbers are 1. So what that would look like on a graph is just a horizontal line at y equals 1. So we exclude that base because it would be a linear graph. It would not look like an exponential function. So let's explore some things with a few different exponential functions. We're going to use our calculator for this. On this first function, my function is 2 to the x. So each of these values I'm going to put into my exponent. So the first one I'm looking at is 2 to the negative fourth. That is 0.0625. Then I'm going to do 2 to the 6/7 power. And I'm just going to do a couple decimals there, 1.8114, and then 2 to the pi. Where's my pi button? I always lose it. There it is. That is 8.825 and on. So both of those go on further. But let's take a look at this. The base of this function was 2. That's a number bigger than 1. And as my exponents increased, my output was also increasing. So that's just something to consider. Let's skip number 2 and go on to number 3. We'll come back. On number 3, my base is 0.25 to the x power. So I am going to find those three values now. 0.25 to the first power, that is 0.25. 0.25 to the 8th. Now this is scientific notation. Remember that e means times 10 to the negative 5 power. So that means this is a small number. When that's negative, that means you're moving your decimal to the left. So there would be 5 zeros here. So this is a tiny number. Now let's do 0.25 to the 25th. And look, this one's even smaller because I've got 10 to the negative 16. So let's look at the pattern here. On this function h, my base 0.25 is smaller than 1, and as my exponents are increasing, my outputs are getting smaller. So let's use that information to make a prediction about this function g of x. I've got 1.085. So should we be getting larger outputs as my exponents are increasing or smaller? So let's take a look. What I'm going to do is I'm going to change this 0.1 to be positive so that we are increasing our exponents. But let's figure out what they are. 1.085 to the 0 power is 1. 1.085 to the 0.1 is 1.0082 and on. And 1.085 to the square root of 2 is 1.122 and on. So again, this base was greater than 1, so my outputs were increasing as my exponent increased. So we call these two examples on number 1 and number 2 exponential growth because my graph is increasing. And on number 3, we call this exponential decay because my graph is decreasing. So let's look at a couple examples of graphs. On part 3 right here, we have a graph that has these two functions, 2 to the x and 4 to the x. We are going to match both and take a look at what the features of each of these graphs is. So let's fill in the table. For 2 to the x, if x is negative 2, my output is going to be 0.25. If x is negative 1, my output is 0.5. If x is 0, I have 1. If x is 1, I get 2. If x is 2, I get 4. And if x is 3, I get 8. Now let's do the same thing for 4. If x is negative 2, I get 0.0625. If it's negative 1, I get 0.25. 0 is 1, 1 is 4, 2 is 16, and 3 is 64. So looking at the graph, my function for 2 to the x has these points. So what I need to do is match them. Here is the point 1, 2. So this darker color graph is that function. which means the lighter color graph is my 4 to the x. So let's look at these two graphs. That generic shape of the curve, that is the shape of our exponential function. And let's look at some of the things they have in common. They are both increasing. That's exponential growth again because my bases are both greater than 1. They both cross the y-axis at 0, 1. That's my y-intercept. And they both approach the x-axis, but they don't touch it. So that's something to consider. Let's go on to the back side and take a look at two more graphs and look at the same situation. So on this one I have graphs for 2 to the negative x and 4 to the negative x. So let's think about what that means and what that is going to look like. Again, I'm going to fill in the table here. For 2 to the negative x, I have 4, 2, 1, 0.5, 0.25, and 0.125. For negative 4, or sorry, excuse me, 4 to the negative x, I have 16, 4, 1, 0.25, 0.0625, and then this is going to be 1/64, which is a really long decimal, so I'm just going to leave it as a fraction. And then again, let's match these on my graph. 2 to the negative x, again, I'm looking at these points. It has the point 1, 0.5, so it is that darker graph. And so the lighter graph is my other one, 4 to the negative x. So let's look at what's changed here. On these two, again, I have that generic shape, but they are both decreasing. We call that exponential decay. They both still have that same y-intercept at 0, 1, and they are both approaching the x-axis, but they're not quite touching it. One thing I want to draw your attention to about why are these decreasing? My bases are both bigger than 1, but these graphs are decreasing. Well, if my exponent is negative, let's think about what that really means, right? If I have a number, say 3 to the negative 2 power, that means it's on the wrong side of my fraction, right? So I would rewrite this as 1 over 3 squared. Well, the same is true here if you have a variable in your exponent. So 2 to the negative x is really 1 over 2x, which is 1/2 to the x power. Now that we've rewritten it with a positive exponent, do you see how my base is less than 1? Same thing for 4 to the negative x. So this is actually exponential decay because if we rewrote it, your base would be less than 1. Now let's talk about what we can summarize from these functions. What was the domain for all 4 of our graphs? The domain for all 4 was all real numbers, and my range was that y was greater than 0. It did not equal 0, and it did not go negative. Now what happened to the value of y as x increased? So what happened to our outputs as our x increased? Well, for 2 to the x and 4 to the x, our graph was increasing, which we called exponential growth. And for the other two, 2 to the negative x and 4 to the negative x, our graph was decreasing, which we called exponential decay. And then our x-axis, remember we were getting close but not touching, that is called an asymptote. So our x-axis acts as an asymptote, and it is horizontal, I should add. And the equation for that is y equals 0. We have a horizontal asymptote at y equals 0, and the y-intercept for all of these was at 0, 1. Now, these are the attributes for our parent functions for exponentials. So let's talk about what could change. What kind of transformations could change? For my domain, if I shift up, down, left, right, or reflect, my domain is not going to change. But for my range, if I have a vertical shift either up or down, that could change my range. Or if I reflect over the x-axis, if I take my graph that's normally exponential growth above the x-axis and I reflect it over that, my y values would become negative. So that's the transformation that could change my range. My asymptote could also change from a reflection like that, or a vertical shift up and down, or a shift left or right. If I initially have a graph like this and I shift it over a little bit, it would cross the axis a little bit later. Sorry, that's down here. For my y-intercept, and then my asymptote would also change for a vertical shift up, down, or a reflection. So these are just things to start thinking about as far as whether we have exponential growth decay, what the default attributes are, and what kind of transformations would change them.